Hey y'all, in this video we are going to go over the vector and scalar notes. So starting off with a scalar. A scalar quantity is a quantity that just has a magnitude. So when I say the word magnitude, I'm talking about the size or the amount of it, the number value. And this will also include the units that go with it. So like for instance, 70 miles per hour that a car would be going, this is a scalar quantity. It's got the number value and then the units that go with it are miles per hour. So other examples would be mass being 5 kilograms, temperature 21 degrees Celsius, speed 65 miles per hour. You notice all of these things, both they have a number value, which is the magnitude, and the associated units that go with it. And that together is your magnitude, and that is a scalar quantity. So a vector, on the other hand, has the magnitude as well as the direction that it's going in. So for instance, if we're going back to that car going 70 miles per hour, that's the scalar quantity, the magnitude. If we add a direction to it, for instance, it's going east, it is now a vector quantity. Other examples could be for acceleration of 9.8 meters per second squared down. That would be a vector, as well as 25 miles per hour west. As long as you have that scalar quantity plus direction, you have a vector. All right, so let's go through some examples and see if you've got an understanding. So 10 meters, is that scalar or vector? Since it doesn't have direction with it, it's going to be a scalar quantity. All right, what about 51 meters per second at 30 degrees north of east? Hopefully you're thinking vector because that's what it is, because it has this direction added to the end of it. For the third one, we have 60 kilometers down. That is also a vector because down is a direction. And then the last one, 8 times 10 to the 8th meters per second, is a scalar quantity because there's no direction included. There's just the magnitude. All right, moving on. From here on out, we're pretty much focused on vectors. Scalars will come back up later in the year as we learn different things. But for right now, we're going to focus more on vectors. So a vector is represented on paper by an arrow. So you're going to be drawing lots of arrows. The length of your arrow represents your magnitude. So that kind of makes sense. The longer the arrow, bigger the magnitude. So if you've got here, which arrow represents a greater magnitude, red or purple, hope you're thinking purple because longer the arrow, greater the magnitude. And then second, the arrow is going to face the direction of motion, which kind of just should be obvious. Why would we point an arrow in a direction that we don't want the motion going, or whatever's going on? Like if it's motion or force, whatever the direction is, that's the way the arrow is going to point, which just is common sense. Right? The third thing is a vector can be essentially like picked up and moved on paper as long as the length and the direction it's pointing does not change. So for instance, I could take these red and purple arrows and move them anywhere on the screen. As long as they're still pointing to the right like they originally are, then they're the same. So what this really comes in handy is when you're working out problems, and if you're drawing all of them out, you can draw them in like your list of vectors in any order and you'll get the same answer. All right. So a couple definitions you need to know. First is the component vector. A component vector is when you have two or more vectors acting on the same point. These normally are going to come up of what's given to you in the question of your component vectors, and then your job is going to be to find a resultant vector. So say I have vector A here in blue, I have vector B in red. You're just one after the next is how you're normally going to draw them. And then you're going to get a resultant vector, which is this one vector that's going to have the same effect as the combined other vectors. So essentially it's like going from the start to finish, the direct path to get there, instead of like zigzagging your whole way there. For component vectors, you're also going to learn how to break down vectors into component vectors, into X and Y component vectors. So for instance, if I didn't give you A and B here, I just focused on this orange C, I can actually break this down into two new vectors called X and Y components. And that'll come up a lot throughout this, this set of notes, as well as future stuff that we're going to learn. So moving on to vector directions. So when we got a vector, you've got to include the direction with it. And there are several different ways we can talk about the direction. There are just straightforward, simple ways, such as right, left, up, down, north, south, east, west. Those are very straightforward and simple. And we'll use these quite a lot, but we'll also get into some more complex ways of saying things going at angles. There are some different ways to state vectors that are going at angles, such as saying it out of 360 degrees on a compass where north is 0 degrees. Or you could go 360 degrees on a coordinate plane where the positive x-axis is 0. Or you could use compass directions where you're giving the degrees off of the north, south, east, or west axis on the compass. An example of how this would be phrased would be 30 degrees northeast. Either of these ways work, and different people like stating them differently. We're going to be straightforward here, and we're going to just stick for the last one and not worry about these other two. Sorry if you like those better. I'm just going to focus on the last one. So, how to use these compass directions. So, my example here is 30 degrees south of east, and that's diagrammed here on, you can call this a compass, coordinate grid, or whatever term you want to use to call this. I'm not really picky. So this 30 degrees is going to be south of east. So of here is telling us which axis it's going to be off of. So this says east. This is the axis I want my 30-degree angle to touch. This first word, in this case south, is going to tell me which way I'm going from east. Like my east axis, I can either go above or north of it, or I can go below or south of it. In this case, I want to be south of it. So that's why my angle is below it. If this said northeast, I'd want to be above, right? From the north axis, I could go east or west. West axis, I could go north or south. And south axis, I could go east or west. So you're going to have how many degrees you're going to go off of. This next one is going to tell you which way to go. And then the last word is going to tell you which axis to touch, right? Get these down quickly because it makes everything easier when you have this, all right? So let's go through some examples. We've got this first one here. It's 50 degrees, and what axis is it's touching? It's touching this north axis, and it's to the west of that axis. So this would be 50 degrees west of north. And you can abbreviate the words north, south, east, and west with just a first letter like this. All right, for this second one, you have 40 degrees, and we're going to look at what axis it's touching, and it's touching the south axis, and it's going to the west of that axis, so it would be 40 degrees west of south. Okay? All right, moving on. We are now going to look at solving for resultant vectors, and there's different methods to do this, and we're going to quickly go through each of them. The first method is called tip-to-tail method. In this method, you're just going to start off by placing your components vectors with the tail at the origin or your starting point, and then draw it in whatever direction it needs to go. And then you're going to place the tail of the next vector to the tip of the previous one. So you're just going one after the next, tip to tail, for as many as you've got. So you place all your vectors, your component vectors down, and then the resultant vector is found by drawing a straight line from the tail of the very first one you drew to the tip of the last one. So let's say I draw this purple one is my first one right here where is my origin. So I draw this one, then this one, and those are all my component vectors. Then my resultant vector is going to start here and end there. So that would be this red one would be the resultant vector. And that's ultimately what I would be solving for. Right? So when you're using tip-to-tail method, if you have vectors just going in one dimension, meaning they're just going horizontally or they're just going vertically, you can add the components up to get when they're in the same direction. So for instance, if I have a vector going 10 meters east, and a second vector, like this next component vector, is 5 meters east, then to get my resultant vector, I just have to add those together, and my resultant vector is just 15 meters east. Which makes sense. If you think of this as somebody like walking down the street, they walked 10 meters east, and then after that, they went 5 meters east more. So how far did they go? 15 meters east. If they're going opposite directions, then you're going to subtract them. So 8 meters west, let's say you walked that, and then you went and walked 3 meters back east. So tip to tail, I just don't want to draw them on top of each other. So my resultant vector would be from here over to here. I'm 5 meters to the west for my resultant vector. Okay, so this works with one-dimensional vectors. It can also work with things vertically, as well as my examples here horizontally. All right, so when you have vectors in 2 dimensions, which we are most often going to work with, is there's some other rules you need to do when you do this. So if you use tip to tail and you want to figure out the answer without doing a ton of math, you're going to need to use a ruler to measure out each vector and use an appropriate scale. For instance, if it's 10 meters, maybe you draw it as 10 centimeters. and you want to use a consistent scale the whole time. And then you're going to use a protractor to measure the angle. So let's say I drew all of these out with a ruler, and you can see this is kind of complicated. I'm going to teach you a better way to do this than drawing it out with a ruler. But you'd have to measure each angle. Like if this is saying it's like, 45 degrees east to south, you'd have to measure that, and you got to be super precise, and then you'd measure your resultant vector. All right, we're not going to get into too much of the technical ways of doing this because it's a lot more efficient to do it mathematically than having to break out a ruler and a protractor. All right, so now we're going to look at finding a resultant vector when you're dealing with things that are right triangles, which you guys are probably going to like these the most because you've learned the math probably in math class, hopefully before this class. So this only works with right triangles. You can have another type of triangle and it's not going to work, and you're going to try and do it anyway, and you're going to get a wrong answer, all right? So the steps to do this is, first and foremost, on every vector problem or things dealing with vectors, sketch it out. In physics in general, sketch out what's going on. You don't have to be super artsy with it. It's just arrows, all right? So you're going to sketch out the vectors. So if it says, 5 meters east and 10 north, you're going to draw that. Then you're going to use Pythagorean theorem to find your magnitude. Now you might be finding the hypotenuse, like I just said with 5 meters, east and 10 north, you'd be finding the hypotenuse. You also could use Pythagorean theorem and solve for one of the legs of the triangle. So that's why sketching out is important, to make sure you know if you're solving for hypotenuse or one of the sides of the triangle. And then to find the direction, you're going to use trig functions to do this, to find the degrees. And then you got to determine like the compass part, the north, south, east, west kind of part of it, because you can't just say 30 degrees. I need to know which way that 30 degrees is going. So on here you have your trig functions. We're going to be using these. Hopefully you've learned them. If not, here we go. Real quick, if you know them, just scoot forward like a couple minutes in the video. But you've got sine is opposite over hypotenuse. So on my triangle here, if this was the angle I was given, or if I'm wanting to find this angle, my opposite side is across from that angle. So that's why it's called opposite, because it's opposite of my angle. And then adjacent side is the side touching my angle, and hypotenuse is the slanted side of my triangle. So if I knew my opposite side and my hypotenuse, I could use inverse sine to find the angle that I'm looking for. If I knew the angle, but I wanted one of these sides, then I'd use the regular sine function. Cosine, if I know my adjacent side and my hypotenuse, I could find my angle by using inverse cosine. And if I knew my opposite and adjacent side of my triangles, then I could use inverse tan. So you would type in, normally in a calculator, it's second, and then sine to get the inverse function, or second and cosine, second and tan, etc. And then you type this in just as shown, right? Now, technically, once you've done Pythagorean theorem, you'll know all sides of your triangles. So you could technically use any of these functions and you should get the same answer. I tend to go based on what sides I'm given in the question. In case I mess up Pythagorean theorem, I just use what's given to me so I don't mess up the angle as well, right? So let's work through an example. We've got to find an object that moves 400 kilometers per hour north and then goes 300 kilometers per hour west. We want to find the resultant vector. And this means I've got magnitude and direction. Don't just do half of it. So first step, Pythagorean theorem. First step is sketching out, but I've already done that for you. And then do Pythagorean theorem. So a squared plus b squared equals r squared, my resultant vector squared. It doesn't, since we're solving for the hypotenuse in this case. So I'm going to 300 squared plus 400 squared is going to equal 250,000 equals r squared. And then I want to square root that. And then I get my answer of 500. So that is my magnitude, all right? And it's in kilometers per hour since that's my units I've been working with, all right? Then for my angle, I have this angle here that I want to find. The angle you're looking for is the angle you first started drawing from. So I first started here and went up. I want to know which way this is going. So I want the angle from where it's starting from, not the angle it's ending at. So I'm going to use inverse tan to find this angle, and that would be my opposite inverse tan, 300 over 400, and that's going to equal 36.9. Technically, you could do inverse sine, inverse cosine, and you should also get 36.9 as long as you're plugging in the correct numbers for each side of your triangle. So now we're going to put it all together, and we end up getting 500 kilometers per hour. That's our magnitude right here that we got up here. And at 36.9 degrees west of north. So that's our direction piece. So that is my final answer. All right, example number 2, we've got a tiger walking 8.485 meters at 45 degrees southeast. So this is going at an angle. When you see this, and if you know for sure it's going to be a right triangle, like I'm going to tell you later, will form a right triangle, that's going to be your hypotenuse, right? Then the tiger goes 6 meters west and find your resultant. So first step, sketch it out. So I know that 45 degrees southeast is going to head down in this direction. And then I go from there, I go west. And I'm telling you it's forming a right triangle, which means this vector needs to end in line with that to make my right triangle, because I'm going to need a right angle here, right? So now my next step is to find my resultant vector. Now that's this red one. It's a leg of the triangle. So for Pythagorean theorem, I'm not solving for C, I'm solving for either A or B. So I left it as B as the variable that I'm solving for and said A was the 6. So that's it set up. I'm going to work out each of the numbers and then subtract the 36 over, and then that equals 36 equals B squared, and then square rooting that, I get B is 6. So my resultant magnitude is going to be 6 meters because my units are going to be the same. All right. Then for direction, I want to know which direction this line is, this resultant vector is going. And it's not going anywhere at an angle. It's just going straight south, right? So if when you're drawing this out and you just see it's going like north, south, east, west, you don't have to do a trig function. You just say it's going south, right? So that's my final answer is going to be 6 meters south. All right, moving on. Now we're going to look at X and Y components. X and Y components we're really going to use them when we're going to essentially break things down into X and Y components. X components are going to be traveling east or west or left or right. North and south are going to be Y components. So horizontal is X, like X-axis is a horizontal line. Y components follow the Y-axis. All right, so it makes logical sense. For negative and positives, we're going to help those also state our directions. So we're going to assign east and north positive. If you think on a coordinate grid, the positive X-axis that lines up with east, west is the negative X. North is in the positive Y, south is in the negative Y. So it makes kind of logical numerical sense, all right? So to do this, first off, sketch your vector and then form it into a right triangle and label the X and Y legs of the triangle. So like if I tell you this blue arrow here, H is the vector you're sketching, then you're going to make it into a triangle. You could do that by going up and over, or you could go over and up. Doesn't matter. Just if you are given an angle to include, just include that there. And then you're going to use trig functions to find the values for X and Y, okay? And we're going to actually do this throughout the year, so this is an important skill to pick up now. So let's work some examples. Okay, so for our examples of solving for X and Y components, our first one example is a vector that's 3 meters per second at 40 degrees north of west. So when you're breaking these down, your first step is to sketch it out. You can either just freehand the vector in the correct direction, or you may find it helpful to put it on like a compass or coordinate plane. And then our vector here is going north of west, so it's going to go off in this direction, and it's going to touch that west axis, and your angle is 40 degrees. All right. Your next step is to enclose your angle into a triangle. So we're going to go over and up to do this, and you're going to label the horizontal side X, the vertical side Y. Now you're going to use trig functions to solve for the values for X and Y. You're probably almost always going to use sine and cosine to do this, and I go ahead and rearrange mine. So normally like cosine is going to be cosine of your angle equals your, in this case, the X side over your hypotenuse. I'm going to go ahead and rearrange this and bring my hypotenuse over to be hypotenuse cosine theta equals X. And the same thing for Y, just replace the X with Y and cosine for sine. So also I left off my magnitude. My magnitude here for my vector is that 3 meters per second that's given to me in the question. So to solve for X, it's going to be 3 cosine 40 degrees equals X. And when we work that out in the calculator, we'll get an answer of 2.3, and that'll be in meters per second. And direction, it would be either going west, or we can put a negative in front of it. And when we do some stuff in a bit, we're going to want that negative there. Then for the y value, it's going to be y equals the hypotenuse sine of our angle. And that's going to be 3 sine 40 degrees. And that's going to equal 1.93 meters per second. And that's headed north, so we can either say north or we can say it's positive. You can write the positive, don't write the positive. It's up to you. Right? Now for the second example, same deal. I'm mainly doing 2 to show you you're not always going to use cosine for x and sine for y. So when sketching this out, it's 15 meters, 30 degrees west of south. So it's going off in this direction, and it's going to touch the south axis. So 30 degrees, your magnitude will be 15 meters. And then you'll want to enclose that into a triangle. And now x is your horizontal, y is your vertical. So now you see that x is across the opposite side, and now y is adjacent. So it's going to be opposite of what we did last time. So to work this out, you have, for x, you're going to use your hypotenuse and then sine, since you want the opposite side. So 15 sine 30. And when you work that out, you're going to get a value of 7.5 meters. And that is going west, so we're going to put a negative with it. And then for the y value, we're going to use cosine, so it'll be 15 cosine 30. And when you work that in the calculator, you're going to get 12.99 meters, and that is going to the west, so we're also going to assign that as negative. So the big takeaways here is just remember you're not always going to use cosine for x or sine for x. It depends on how your triangle is oriented. So that's why it's important to sketch it out so you know which one to use, right? And also make sure you include those negatives when it's going west or going south. Now, when we're solving using x and y components, like we could just break things down into x and y, and later in the year we're going to do different things with them. But when we're solving just a vector problem, we're going to using this x and y component method, we're going to determine if the x and y we're going to determine if the component vector is an x or a y component, and we're going to add a positive or negative as needed. And then we're going to add up all the x's and add up all the y's. Essentially, this gives us the resultant x value and the resultant y value. And then we're going to turn this into a right triangle using x and y totals, right? And then from here, it's like solving a regular right triangle problem. So like when we went way back to, we're going to skip back way back here. This is not an efficient way to do this. When we get to a problem like this, and I give you this huge list and you have to draw out all this, and you're like, I don't want to use a ruler and a protractor, the x and y component method is the way to do this, right? And we're going to skip forward again, and you're, all right. So doing that, this is the way to do that, okay? So now we're going to work out this example. And all right, so let's work through this example of solving with x and y components. So this example gives you a list of component vectors, and it's set up in a table. They won't always be set up in a table, but this is just a useful tool to solving these types of problems. So first up, we have our first component vector is 5 meters north, and we want to break that down into x and y components. When something's just going north, south, east, or west, you don't have to break it down into x and y components like we did in those earlier examples. You just simply move it into one of the columns. So for north is going to be a y component, and it's positive, so it's just going to slide over here into this column, and you can put a 0 in the x column or just leave it empty. That's personal preference, and that's up to you. For the next two vectors, they're going in an angle, so we're going to break those down like we did in the earlier examples. So I'm not going to go through all of the steps on how I'm going to do this. You can go back to the earlier examples if you're sure not how to do it, but you would want to sketch them out. So for instance, the first one is going to go down at an angle. It's south of east, so it's going to look like this. Of your hypotenuse is 12 and then 35 degrees. And then I'm going to use enclosure triangle, x and y. And so for x, I'm going to do 12 cosine 35. equals 9.83. And then for the y would be 12 sine 35, and that's going to equal 6.88 in the calculator. But since y is going in the south or negative direction, I want to make it negative. And then I'm going to take those numbers so take the numbers of what we just did, and we're going to add those into the chart. So the x component goes in that column, so 9.83, and then negative 6.88 in the y. All right, now you're going to repeat for the next vector. You're going to do the same steps. I'm going to quickly just draw it out. So 14 meters west of south is going to go off like this. It's going to be a hypotenuse of 14, an angle of 60 degrees, and then make that into a triangle. And this time my triangle is oriented a different direction. So now x is going to be 14 sine 60, and then y is going to be 14 cosine 60. So when you solve for this, you're going to get 12.12 in the calculator for x, but it's going west, so we're going to make that negative. And then for the y is going to be 14 cosine 60 is going to equal 7, and we're going to make that negative because it's headed south. So again, anytime something's going west or south, you make a negative. Then we're going to take those numbers and put them into our table. So negative 12.12 and negative 7. And now we've done all that. So now the third step we've got here is going to be to add up each column. So we're going to add up the x column, and that's going to equal negative 2.29. And we're going to add up the y column, and that equals negative 8.88. So now we can make that into our triangle. All right, so from here, it's just like a right triangle problem, and those two numbers are going to be the legs of your triangle. So for the x vector, you are going to, since it's negative, we're going to go west. If it was positive, you'd go east. Then at the end of that, you'll draw the y one. If it's positive, you go north. In this case, it's negative, so we're going to go south. All right, and then label them with the magnitudes. From this point, the negative signs don't matter. Now, you can draw the y first and then the x. That doesn't matter. I personally draw x first, then y, because they're written in that order. And then our hypotenuse is going to be the resultant vector that we want to solve for, and we want this angle here where that one starts at. So, like I said, from here, it's a right triangle problem. So you're going to do Pythagorean theorem of 2.29 squared plus 8.8 squared to get r squared, and then, sorry, I'm running out of space here, r squared. And so solve for r, and it's going to equal 9.17 meters. That's your magnitude. And then direction. Technically, I can use any trig function because I now know all three sides of my triangles. But personally, I like to use inverse tan for this because that's the two legs of the triangle. So it's going to be 8.88 over 2.29 is equal to my angle. And that angle is going to equal 75.5 degrees. So now we want to put all of the pieces together. Sorry about this. So we want to take the magnitude that we got of 9.17 meters, and then we're going to have it going at a direction of 75.5 degrees, and then we want to know which way that's going. And if we look back at our sketch, and if I put this like on a compass, I can see that 75.5 is touching the west axis and it's below it, so it'd be south of west. So that is my final answer for this problem. So these are a whole lot of work. They get easier as you do more and get more practice. But yeah, that's it.